My name is Gnana Saurya Vankayalapati. I'm a PhD student in the MEME graduate program. And the title of my presentation is Nanocellulose Fibers as a Reinforcement to Improve the Strength and Toughness of Structural Materials. For better or for worse, a lot of products that we use daily are made of plastic. The ease of manufacturing and the robustness means that the plastic consumption is expected to grow with no any immediate signs of slowing down. Plastics do not make sense environmentally, but they do make a lot of sense economically. And therefore, it is very important to both improve the efficiency of how we use plastics and also try to come up with degradable alternatives to plastics. These are the two questions I try to answer in my research, which is focused on using nanofibrillated cellulose, or CNFs as we call them, to enhance the strength and toughness of polymers. And all throughout my work, I focus on a term called fracture toughness, which is a very important material property, and enhancing it without adversely affecting the strength is a very challenging materials problem. In the first part, I fabricate composite materials where nanoscale fibers are reinforcing the PMMA polymer matrix. We use the approach of solvent blending and melt spinning together to fabricate a one-dimensional composite fibers. And I showed that adding CNFs increases the strength, and most importantly, it increases the fracture toughness of the PMMA by almost 100%. And now, in order to incorporate higher compositions of CNF in these composite systems, I used a novel approach of amination along with the cross-linker reaction to realize composites or to realize laminates made of PMMA and CNFs. The second goal of my research is to realize fully degradable alternatives to thin plastic sheets. And in here, I fabricate composite sheets made of cellulose of different length scales. Reinforcing papers with CNF does increase the strength, and I optimize the patterns in which CNF is deposited on paper to tune or to improve the fracture toughness of the whole composite sheet. Through finite element simulations and a few experiments so far, I've shown that adding CNFs and introducing this elastic heterogeneity can improve the fracture toughness and strength simultaneously. The final step in this thrust is to develop a framework based on cohesive zone finite element modeling to predict or to estimate the fracture response of these heterogeneous cellulose sheets. In summary, through my research, I use nanoscale cellulose fibers to improve the mechanical properties of plastic and also realize fully degradable alternatives to thin plastics. My work here not only addresses the mechanics problem of fracture toughness and strength, but also provide an additional market for US biomass resources and hopefully help reduce forest waste.